Welcome to this explainer where we're jumping straight into the hidden tech that literally runs our modern world. You might never actually see them, but they're absolutely everywhere, quietly keeping civilization functioning day in and day out.
I mean, really think about it. What actually controls the modern world? When you picture the hyper-precise robotic arms in a gigafactory, or massive city water treatment systems, or, even the baggage carousels sorting thousands of suitcases at an airport, how does it all coordinate? It's definitely not magic, and it's rarely just a human sitting in a control room flipping physical switches anymore. Instead, I want you to consider the unassuming, rugged little boxes orchestrating all of this massive physical movement. We're talking, of course, about programmable logic controllers, or PLCs.
So, to fully understand exactly how PLC systems work today, here's our game plan. We're covering 1. The invisible industrial brain. 2. Inside the PLC architecture. 3. The 3-step scan cycle. 4. Programming and communication. 5. PLCs in the real world. And 6. The future of automation.
Section 1. The invisible industrial brain, from chaos to control.
To really grasp how PLC systems work today, you kind of have to picture the historical nightmare they replaced. We're talking about relay logic. Imagine factories relying on massive control rooms filled with literal miles of tangled wires and thousands of mechanical relays just constantly clicking away. If you wanted to change a single manufacturing process, you had to manually trace and rewire the entire factory floor. It was a total nightmare to fix and prone to constant breakdowns. Enter modern PLCs. They're software-based, highly compact, and incredibly easy to update. Instead of shutting down a plant to rewire a room, an engineer literally just updates the code from a laptop. It catapulted manufacturing from mechanical chaos straight into sleek, programmable efficiency.
Section 2. Inside the PLC architecture, anatomy of a controller.
Let's lift the hood and look at the hardware. It actually helps to break down this highly technical box using a biological analogy. The CPU, or central processing unit, is the absolute brain of the operation. It does all the heavy logical thinking. Then you have the memory, acting as the brain's knowledge center, storing the engineer's program and keeping track of the system's current state. Of course, you've got the power supply keeping the whole system alive, communication ports acting like vocal cords to talk to other machines, and expansion modules, which are amazing because they let the system grow and adapt as a factory expands.
But to really ground this in reality, we have to look super closely at the input and output modules, which you'll always hear called I/O. Think of the input modules as the senses of the PLC. This is where it actively detects the physical world. It feels that an emergency button has been pushed, senses a sudden temperature drop, or notices a proximity sensor has just been tripped. The output modules, on the flip side, are the muscles. Once the brain makes a split-second decision based on those senses, it uses the outputs to take physical action. It tells a heavy-duty motor to spin up, forces a conveyor belt to halt, or commands a traffic light to instantly turn red.
Section 3. The 3-step scan cycle, the heartbeat of automation.
Okay, so the crucial point is how this hardware actually thinks and acts in real time. And it all boils down to a continuous, relentless loop. Step 1. Read inputs. The PLC checks the status of all its sensors. Step 2. Execute program. The CPU quickly runs through the exact logic rules the engineer wrote. Step 3. Update outputs. It fires off the commands to the muscles of the system. Read, execute, update. Read, execute, update. Read, execute, update. This happens in milliseconds, continuously, without ever stopping to take a breath. This lightning-fast, highly predictable cycle is exactly why PLCs are trusted with mission-critical tasks where even a millisecond of delay could literally spell disaster for a production line.
Section 4. Programming and communication. Talking to the machine.
So we know how a PLC thinks, but how do we actually give instructions to these devices? Whether you're programming a simple start-stop motor or managing a crazy multi-floor elevator system, engineers rely on the IEC 61131-3 global standard of programming languages. Ladder logic is massively popular here. It was intentionally designed to look exactly like a visual wiring diagram, which beautifully bridged the gap for electricians transitioning from the old relay logic days. Then you've got function block diagrams, structured text for folks who prefer traditional computer coding, sequential function charts, and the historical instruction list. Depending on the task, engineers pick the perfect language to tell the PLC what to execute during that rapid-fire scan cycle.
But remember, a modern PLC doesn't work in isolation. It relies on a whole alphabet soup of industrial communication protocols. Things like Modbus, Profibus, Profinet, Ethernet IP, CAN bus, and OPC UA.
These are basically the networking languages machines use to talk to each other over a factory network. This is exactly how PLCs integrate with larger SCADA systems. You know, those massive control room screens you always see in movies, and human-machine interfaces, or HMIs. It brings the whole operation into a unified, visible dashboard for the human operators running the show.
Section 5. PLCs in the real world. Global automation applications.
Let's zoom back out to the macro level to really appreciate the massive scale of what these tiny scan cycles achieve. The sheer scope is staggering. We're talking automobile factories, food processing, chemical plants, oil and gas, robotics, smart factories, packaging, power plants, water treatment, and airports. The versatility of PLCs in everyday life is just endless. Whether it's precisely mixing the ingredients for your favorite snack, choreographing giant robotic arms, welding a car chassis together, or just making sure the water coming out of your tap is perfectly safe and pressurized, there's a PLC quietly running the logic in the background.
And because these applications are so incredibly diverse, one size definitely does not fit all. PLCs scale all the way from tiny nano and microcontrollers for simple standalone machines, up through compact, modular, rack, soft, safety, and heavily redundant systems. Those redundant ones are used in massive power plants where a system failure is absolutely not an option. Major industrial brands like Siemens, Allen Bradley, and Mitsubishi Electric are building these specific form factors for absolutely every industrial need and complexity level you could possibly imagine.
Section 6. The future of automation, beyond the box.
We've seen how they work today, but looking at the horizon, the modern PLC is moving way beyond simple if this then that logic. Today we're seeing the deep integration of artificial intelligence and the industrial Internet of Things, what's often called Industry 4.0. We're talking about edge computing, where heavy data is processed right on the factory floor rather than in some distant cloud. We're even seeing the use of digital twins. These are highly detailed virtual replicas of a physical factory that allow a PLC to essentially run simulations and predict mechanical failures before they ever happen in the real world. The traditional boundaries of what a controller can do are expanding exponentially.
Which leaves us with this final thought to ponder. As digital twins and artificial intelligence continue to merge deeply with industrial hardware, just how smart will these invisible controllers become? We've gone from miles of tangled relay wires to self-optimizing, predictive industrial brains in just a matter of decades. The evolution of automated systems is unstoppable. So the next time you turn on a light, drink a glass of water, or buy a manufactured good, I hope you remember the incredible little boxes that made it all happen. Thanks for joining me on this explainer, and keep questioning the world around you.